So let's look at a few problems that are a little bit more difficult. Notice we have this function g of x where we have quadratics in the top and the bottom. And most of the work for these problems is going to be factoring. And in this one especially, we'll have to factor the top and the bottom so that we can see if we can make any cancellations, or we can see which values of x would make this denominator equal to 0. So we have x squared plus 4x minus 21 in our denominator. And we'll set up our product of two binomials in the top and in the bottom. So let's start with the top one. So notice that the coefficient on x squared is 1. So that means this has to be x, and so does this, so that you can get x squared. Now we can also notice that these next two terms in our binomials here, these will multiply to give us negative 14, and they will add to give us 5. So let's write out a list of those. So to get minus 14, you can do minus 1 and 14. You can do 1 and 14. You can do, negative 14. You can do 2 and negative 7, or you can do minus 2 and 7. And again, one of these pairs has to add to 5. So in our case, it looks like negative 2 and 7. Of course, you can check these as well. Just redistribute and prove to yourself that it is equal to this top expression here. So let's now do the bottom one. We'll use a different color for that. It's also a product of two binomials, and this has to be x, and so does this, so that we can get x squared. Now in this one, they need these two numbers here, this one and this one, the constant terms, they have to multiply to negative 21 and add to 4. So we'll make out our list. So to get negative 21, you can do minus 1 and 21, 1 and minus 21. We can do 3 and negative 7, or minus 3 and 7. And these have to add up to positive 4. So that's going to be minus 3 and positive 7. So right away, looking at this function in factored form, you can see that x cannot be 3, since you'd end up with 0 times 10, which is 0, and x can't be negative 7. So both of those values are not in our domain. So we can say that x cannot be 3 or negative 7. And we just need to determine, are they vertical asymptotes or are they removable discontinuities? And remember that these removable discontinuities, you can always make a cancellation like you can with the x plus 7 terms. So that tells us that at negative 7, we really have a hole in the function, or this removable discontinuity. However, at 3, since you can't make a cancellation there, we can assume that's a vertical asymptote. And then lastly, at 2, so if you plug the value of 2 into the function, notice you get 0 times by 9 divided by negative 1 times by 9. But 0 multiplied by anything or divided by anything is 0. So at 2, the function is equal to 0, and so this is one of our zeros, or our x-intercepts. And I encourage you, pause the video, plug this into your graphing calculator, and prove to yourself that these conclusions actually made sense. So let's keep going. So for this one, we have that q of x is equal to x squared plus 6x plus 8, all divided by x plus 4. And right away, we can see that x cannot be negative 4, since if you plug this in here, you would get 0 in the denominator. So we just need to figure out, is that an asymptote or a discontinuity that can be removed? And to determine that, we just need to factor this numerator. Let's do that down here. We'll write the numerator as a product of two binomials. And we know the first term in each of these, since there are two terms in each, it's going to be x and x, since that's how you get x squared. And we know that the next two terms, this one and this one, these are going to be numbers that will multiply to 8 and add to 6. So we can write out our list. What multiplies to 8 could be 1 and 8, 2 and 4, or it could be the negatives of each of these, but it's adding to a positive number, And you can see that 2 and 4 would add up to 6. So this would be plus 2 and plus 4. Now notice that we have x plus 4 in the top and the bottom. So since we can make this cancellation here, we know that at -4 it won't be a vertical asymptote, it'll be that removable discontinuity. So if we graph this, we'll get a hole in the function at the value of -4. So that's a removable discontinuity. And then if we plug in -2, notice that's going to make our numerator equal to 0. So q of -2, you get 0 times by 2 divided by 2. And 0 multiplied by anything is 0. So that would just be equal to 0, and -2 is one of our zeros. So let's do one final problem. And we have this function p of x is equal to x squared plus 10x minus 11. And we have x minus 11 in the denominator, which tells us right away that x cannot be 11. Since if we plug in 11 here, we get 0 in the denominator, which we cannot divide by. So that's either this asymptote or the removable discontinuity. And to answer that question, of course, we need to factor this numerator. So we'll write our product of two binomials where we know each of the first terms is x, since x times x is x squared. Let me just rewrite the bottom. And we just need to figure out these number terms here. So these missing number or constant terms, they're going to multiply to -11, and they're going to add to +10. So that could be -1 and 11 or 1 and -11. And you can see that -1 and 11 do add up to 10. So this would be -1 and plus 11. And what you can see is that we don't have the same factor, this x minus 11, in the top and the bottom. We have x plus 11 up here and minus 11 here. So we're not able to do a cancellation like that, which tells us that for an x value of 11, this is a vertical asymptote. So we know that. And for the other two, when we plug those into the function, so let's plug in -11 first, that makes this factor here equal to 0. So we'd get -12 times 0 in the numerator, which is 0. So that's one of our zeros of the function. And when we plug in 1, that makes this term 0. So you get 1 minus 1, which is 0, times by 12, and 0 times 12 is 0. And of course, 0 divided by some value that isn't 0 will always result in an answer of 0. So this is equal to 0 as well. And both of these, since they made the numerator 0, or the function equal to 0, these are the zeros, or the x-intercepts, of the function. So each of these, we have a 0. And since this is our last one, let's check it with a calculator. So we want to look at the graph of this. So let's put in this function here, p of x, and we want to take the entire numerator. So x squared plus 10x minus 11. And we're going to divide by the entire denominator, this x minus 11. And since we don't know what this is going to look like yet, let's just do a standard zoom. So zoom 6. And we can see one of the zeros at x is equal to 1. Let me just scroll this over so we can see it more. So if we trace this and put in 1, notice that we do get 0. So that one made sense, but let's zoom out a bit so that we can see the rest of it. So that's zoom 3, and we'll scroll over. And now if we trace and we put in -11, we can see that we get our other 0. Now we need to figure out what happens at 11. So if we trace and we put in 11, we can see it's not defined, but it's hard to see if this is an asymptote or not. We do see the function shooting off down to -infinity. Like for instance, if we put in, let's say 9, that's a value of -80. And then if we trace and keep going, it keeps getting bigger and bigger in the negative direction. And once we go to the other side, notice it's positive. But we do want to visually confirm this, so let's just zoom out again. We'll do zoom 3, and let's scroll down a bit. And there you have it. You can see that we do have this vertical asymptote at 11.